So folks, welcome to Dynamic Earth. Today we're going to be talking about really big picture ideas. We're going to be talking about really the origin of the universe and the origin of our solar system. And this is really sort of the beginning of our planet in here. Um, and so that's what we're going to be, or I guess the lecture today is going to be divided into sort of two different parts. First part focuses on really sort of the origin of the universe. Second part, I will basically do a tour through the various planets in our solar system and think a little bit about how other planets in our solar system are different or similar to Earth. And so that's what we're going to be doing today. Share my screen here. Okay, so one thing to think about here is the Earth is a planet. We're going to be spending most of the semester talking about various processes on the Earth, but the Earth is just one of many planets. There's 8 sort of major planets in our solar system, a number of minor planets. We've also discovered planets in other solar system. We've discovered thousands of them in the last 20 or 30 years or so, and that's relatively new discovery in terms of science, that there are planets elsewhere orbiting around other stars and so forth. But still, the Earth is unique in its ability to support life. We haven't discovered life anyplace else in the universe. And so it's a unique and sort of special place, and even more so because it's our home. So today we're going to talk about sort of some really big picture ideas, like I said. The biggest of these is sort of the origin of the universe. And the current theory for how our universe formed is this idea known as the Big Bang. And this is the idea that all matter and energy was at sort of a single point in the deep past. And then basically, for whatever reason, there's no sort of scientific known sort of reason for it. Basically, you had an explosion, the Big Bang itself. And this is considered the beginning of the universe. Science really cannot see past the Big Bang, and so what has gone on previously is basically a mystery. But there's fairly good lines of scientific observational evidence that the Big Bang did actually exist, and we'll talk about one of those. The first person to postulate the Big Bang and discover some of these first lines of evidence was a scientist by the name of Edwin Hubble, and he worked in sort of the first decades of the 20th century. And in sort of the 20s and 30s, this idea is really big, basically was first proposed. And what Hubble made observations of is he made the realization that there were other galaxies in the universe, not just the Milky Way, and that all of these galaxies are moving away from each other. And so if you take the motion of these galaxies and you basically project them back in time, at a certain point they project back to a single point. And this is considered sort of the Big Bang, or the beginning of the universe. And subsequent observations have continued to support this idea. And so we now can put together a timeline of the Big Bang. There's basically a time zero for the universe. And at this point, all matter and energy is concentrated sort of at a single point in the universe. And then basically you have the Big Bang itself. The universe begins to expand. Initially, it's sort of extremely hot. You don't have sort of individual atoms. You've got sort of this soup of subatomic particles known as quarks. But as the universe expands, it begins to cool. And eventually you begin to form what we consider regular matter, sort of atoms with electrons and protons. And this happened at around 300,000, 3 to 400,000 years after the Big Bang. And it's at this point that basically you go from having this plasma everywhere to having sort of individual atoms. And it's also at this point that the universe becomes transparent to electromagnetic radiation. And there's sort of an afterglow of the Big Bang that we can see everywhere in the universe. And this is something known as this cosmic microwave background radiation. And we'll talk about more, but this is sort of an important point, that it's basically a confirmation of the Big Bang. And so the Big Bang was first proposed to exist on the motion of basically galaxies and basically being able to track these back to a single spot. And then a prediction was that this sort of microwave background radiation existed. But it wasn't until the 1960s that people were able to develop good enough radio telescopes to really detect this. And so this was considered a big confirmation that the Big Bang actually existed. And then after that, basically you had this matter gravitationally condensed to form stars, and stars grouped together to form galaxies, and eventually we have the universe that we see today. There's another sort of view of this sort of expansion of the Big Bang. You've got the Big Bang itself, and this period of inflation where the universe sort of greatly expands its size. And then you have this cosmic microwave background radiation, this sort of afterglow of the Big Bang itself. This diagram is 380,000 years after the Big Bang. And then you have first stars about 400 million years, and then sort of galaxies and so forth begin to form in here. So we've sent satellites up into space that have mapped out this microwave background radiation in detail. There's been several different satellites that have gone out and done this. This map here is, you can think of it as sort of a map of the night sky, but it's looking sort of beyond all of the stars and so forth, and looking at sort of this background radiation in here. And so after this formed, the universe continued to expand, and this microwave background radiation, it was initially at a temperature of sort of 3,000 degrees, but has then subsequently cooled to 2.7 degrees Kelvin. That's 2.7 degrees above absolute zero. That's the coldest you can be in the universe. And that's sort of the background temperature of the universe and space. And based on sort of the distribution of basically this background radiation and how it's been stretched out and the patterns that we see in it, people have been able to calculate an age, a more precise age for the Big Bang. And this is 13.8 billion years ago. And that's currently about the best accepted time for the origin of the universe in here. So the Big Bang itself is fairly well accepted, that you've got these two major sort of observational bits of evidence that support it. There are still sort of unknown features of the universe. About 5% of the universe is what we consider normal matter that we can see, basically stars and so forth. About 30% of the universe is something known as dark matter that's needed to explain basically gravitational attraction between between galaxies and rotational aspects of galaxies themselves. And then there's something known as dark energy that's needed to basically explain the rate of the expansion of the universe that we see. And what dark energy is also really sort of an unknown thing. And so last time we talked about sort of scientific paradigms and so forth. And this is one scientific paradigm. This sort of concepts of dark matter and dark energy are something that may be subject to a scientific paradigm in the future, although it's sort of the current best explanation that we have. If we look back into space, we are looking back into time. And the reason for this is that the maximum speed that anything in the universe can move at is the speed of light. And so anytime we look out in the world, we're looking back in time. If we're looking at each other, say on Earth, we're looking basically at a few milliseconds, basically the time that light takes to reflect off an object to get to us. But if we're looking out in space, we're looking back in time. And so the light that we see from the star takes about from the sun takes about 8 or 9 minutes to get from the sun to the Earth. So we're not looking at the sun now, we're looking at like 8 or 9 minutes in the past. And likewise, if we look to distant sort of stars and galaxies, we're looking even further back in time. And so we can take pictures of essentially empty spots of the night sky and look very far back in time and look close to the time of the Big Bang. And so what we're seeing here is an image from the Hubble Space Telescope that was pointed at an empty region of space, and they just opened it up, let it collect light for a long period of time. And we can see galaxies that are basically within 1 billion years of the Big Bang itself. So galaxies that are like, say, 12 billion years old in here. And so if you look out into deep space, you can not only look at things that are far away, you can look at what the universe looked like close to the Big Bang itself. Uh, so Hubble here, Edwin Hubble discovered basically this expansion of the universe and came up with this idea of the Big Bang. And one of the primary things that this depends on is this idea of a redshift of basically the light from stars. And so this takes into account the Doppler effect. And what this is, say if a car goes by you, you can hear the noise that it sounds. And as the car passes you, for instance, the sound that the tires are emitting will move to a lower frequency. And so as an object is moving towards you, waves that are emitting are compressed and move to sort of higher frequencies, where if it's moving away from you, they're extended to lower frequencies. Same thing happens with light in here. And galaxies that are moving away from us have the light. Say if you have a galaxy or a star of a known distance, and you know what type of light it should be emitting, but it's emitting, say, light a longer wavelength, then you can figure out that this thing is moving away from us in here. And this is known as the Doppler effect. And basically, galaxies everywhere are moving away from us. This is another sort of a deep space image. This is an updated one from the James Webb telescope in here. You can also see sort of interesting things like gravitational lensing and so forth, light bending around sort of other stars, other sort of these smeared out things. But you can see galaxies here that are 12, almost 13 billion years old. And so basically we can measure the light in these galaxies. And what's shown here is basically sort of the redshift of these galaxies. And so there's a galaxy here that's say 13 billion years old. And basically the light in it is shifted to longer wavelengths. And so that's how we know that it's how these things are old. Okay, so there's a couple of different options for how the universe could be. That basically, before people started making observations of what sort of different galaxies and the motion of these things, one option was that you have a static universe that just sort of sits there. And in this, you'd expect galaxies to have sort of random motions and so forth, but that's not what we actually see. What we observe is this observation that galaxies everywhere are moving away from us. And so this is interpreted that we've had this sort of expanding universe, and you can project the motion of these galaxies sort of back in time to a time zero that's the Big Bang. And not only that, if we look at things that are farther away, we see that they're moving away faster in here. And so say, for instance, if a galaxy is 1 million light years away, it might be moving away from us at 15 kilometers a second, whereas if a galaxy is 2 million light years away, it might be moving it away at 30 kilometers a second from us in here. And so how people inverted this to find sort of the age of the universe is that you can use sort of a simple equation here. Rate equals a distance divided by a time. And if you can measure the distance to that object and you can measure the rate at which it's moving away, basically you can come up with a time. And basically you do this measurement for a whole bunch of different galaxies, project them back in time. And when people sort of first did this, you got ages that range from about 10 to sort of 20 billion years. They're a pretty big age range in here. But as these measurements of sort of the rate at which these galaxies have been moving away, and then also the distance to them, as these things have improved, basically the estimates of when the Big Bang happened have also improved. Okay, so that's the origin of the universe in here. So the Earth is a planet. It's in orbit around the sun, and the sun is part of the Milky Way galaxy. And this is interpreted to be basically a spiral galaxy. This is not actually a photograph of the Milky Way because we're within the Milky Way galaxy, but it's approximately the same size and interpreted shape in here. And so we live in sort of the outer arms of this galaxy in here. And the Milky Way is characterized by having a big central bulge that has lots of stars in it in here. There's about 400, there's billions of stars within sort of the Milky Way itself. We can think about why it's called the Milky Way galaxy, and I'll show some images. It basically makes a band through the sky in here. And one of the things we've come to realize is that at the center of most galaxies there exists sort of a supermassive black hole, and the stars in the galaxy are in orbit of it. The galaxy, or the supermassive black hole in the Milky Way, is known as Sagittarius A, has a mass of about 4 million suns in here, and we can see it basically periodically sort of eat material, and then it emits energy when it does so. We can also track basically the orbits of stars and so forth around it to get an idea of its mass in here. And so this is definitely a real thing that we can observe in real time. Okay, if we look out at the night sky, you can see the Milky Way in here. It's this band of skies. This is in sort of Death Valley in California, in the middle of the desert. You can see this galactic bulge in here. That's where this Sagittarius A supermassive black hole actually lives in here. So another view of the Milky Way from Earth. And so we're sitting in basically this galactic sort of plane in here. You can see the galactic core. Our nearest neighbor is the Andromeda Galaxy. It's also basically it's a disc-shaped galaxy. You can see it has a galactic core in here as well. It's 2.5 million light years away. And so it might be conceivable at some point to reach sort of another star system the nearest one is about 4 light years away. But reaching another galaxy is basically entirely beyond any sort of technology that we can really sort of conceive at this point. But there are millions of galaxies in the universe. So our universe is incredibly large. There's another sort of galaxy in here. Okay, so periodically I'll have these sort of what you should know slides. This first part, you should know what the age of the universe is, 13.8 billion years. I should know that it formed via the Big Bang, and that the two primary data sets that support this are sort of the Doppler effect and sort of the redshift, basically, of sort of galaxies due to sort of the expansion of the universe, and then this prediction of sort of this cosmic microwave background radiation that we found to exist. So those are sort of the most important things you should know from this first part of the lecture here. Okay, so now we're going to move on to our solar system. And so the Earth is the largest of the 4 rocky inner planets in here. Most of the mass of our solar system, something like over 99.5% of the mass of our solar system, is in the sun in here. And so the planets are sort of rounding errors in it, but the Earth is important to us. So we've got 4 rocky inner planets: Mercury, Venus, Earth, and Mars. We've got 4 outer gas giants: Jupiter, which is the largest planet in the solar system, Saturn, Uranus, and Neptune. Pluto used to be considered a planet, but has now been downgraded to a dwarf planet status in here. And there's several of these dwarf planets. We've got Ceres in the asteroid belt, Pluto, Eris, and potentially several others in sort of the outer sort of reaches of the solar system in the Oort cloud out here. The Kuiper belt. So here's just sort of a scale model of the solar system itself. 1 astronomical unit is basically the distance from the Earth to the sun. So the total width of our solar system is about 200 AUs across in here, with the Earth being sort of really pretty close to the sun itself. Okay, so there's the Big Bang theory. That's our theory for the origin of the universe. The other big theory that you should know, origin theory, is the solar nebular hypothesis. And This is the idea that our solar system formed from this cloud of gas and dust, and then the sun ignited about 4.5 billion years ago. And by ignited, I mean that the pressure in the sun became so great that you initiated thermonuclear fusion, and that's considered the beginning of the sun. And so everything in our solar system is made up of elements and materials that were formed in other stars, stars that lived and died and basically blew up before the existence of our solar system in here. So there's been multiple generations of stars that have lived and died, and all of us, everything on Earth, is literally stardust in here. So this cloud of gas and dust began to form probably about 6 to 7 billion years ago in here. And under gravitational attraction, one, say, molecule of hydrogen, another molecule of hydrogen became to be attracted to each other and then stuck together. And then this process sort of accelerated as masses got bigger under gravitational attraction, and you formed the sun, and then you had other loci of sort of gravitational attraction that formed the planets in here. This is sort of a solar example of, say, the formation of sort of an individual nebula in here. And so you've got a cloud of gas and dust, and something like this might have happened when the sun ignited. And so it pushed this sort of cloud of gas and dust into the outer reaches of the solar system. It's one of the reasons why you have sort of the inner rocky planets and the outer gas giants. Another sort of illustration here. So you've got this initial cloud of gas and dust. It concentrates itself gravitationally, and then the sun ignites, and that's the beginning of our solar system. And the inner planets are enriched in heavier elements, and that's because all the lighter elements have been basically pushed out in the outer solar system by the solar wind in here. That's sort of energy and particles streaming off of the sun in here. And so the inner solar system is enriched in heavy elements, things like iron, silicon, magnesium, aluminum, oxygen, and so forth, where a lot of these sort of volatile compounds, things like helium, hydrogen, water to a lesser degree, nitrogen, methane, and so forth, a lot of these were pushed more completely into the outer solar system. And those formed the gas giants in here. So here we've got the sun, and then these separate sort of loci of attraction in here that form the individual planets. Here we've got sort of your initial sort of protosun shortly after ignition. You've got your accreting rocky planets, and then outer solar system you have your planets that begin to form your gas giants, and they're sort of separated by this frost line. Okay, so we're going to do a tour of the planets in our solar system, but before that, we're going to take a slight detour and talk about planets on other solar systems, because this is sort of it's something that's, I think, important to be aware of, that our solar system is not unique. Most stars we now know probably have planetary systems around them. We're limited in basically what we can detect, because we can only detect planets that are in certain orientations at sort of certain distances to Earth in here. But we've discovered thousands of these things. And really the goal is to see if we can discover another planet like Earth, and potentially another planet that might harbor life in here. And how we actually detect planets on other solar systems, for the most part, they're too small to see optically. But say if a planet orbits in front of a star, it'll cause a decrease in the amount of light that basically comes to us. And so we've put dedicated sort of planetary satellites sort of out in space that basically stare at different stars in our galaxy. And when a planet goes in front of them, you get this decrease in the amount of light. And basically, if you get sort of 3 regular decreases like this is interpreted to be basically an orbit of the planet around the star. And then from that, you can figure out sort of how, basically the mass of the planet. Sometimes one of the goals is to basically be able to spectroscopically measure some of the light coming through the atmosphere to figure out, say, the composition of it, see if there's something like oxygen in the atmosphere, So you could detect basically, or maybe have an inference for the presence of life. So most planets are detected basically sort of by these sort of secondary means. A couple of planets have been imaged directly. One of these is from this planet Fomalhaut b in here. It's a planet star that's about 25 light years away, but it's just a few pixels of light that's been measured and observed in here. Another view of it with some infrared light. Okay, so most of these planets, there's a wide variety of different things that have been discovered. Some of them are rocky planets, some of them are these lava worlds, basically like liquid rock and so forth at the surface of them. Some of them are like the size of Jupiter. Some of them are these ice giants and ocean worlds. Most of them, though, are bigger than Earth and also very close to the star. It's more sort of an artifact of what we can actually discover than necessarily the true distribution of planets in the universe. Because say if even to discover the Earth, basically if you need 3 orbits, you need to stare at basically the solar system for a minimum of 3 years in order to detect basically sort of your Earth in here. And if it's say out where say Mars is, for instance, it has a year that's twice the length of the Earth, and you need to stare at it for 6 years. And that's basically sort of the limit of basically these types of measurements and so forth that we can do. It's also a really small part of our galaxy that we've been able to look. We've only been able to look maybe within, say, 300 light years of the Earth itself. But the main point here is that there's lots of planets in the universe. And really, one of our goals is to see if we can discover another Earth-like planet someplace in the universe. And an ultimate goal of science would be to determine if there's life anyplace else in the universe. So far, we've not discovered life anyplace else. Earth is the only spot. Okay, if we go back to our solar system here. So we're going to be talking about, basically we're going to look at some of the characteristics of each of these different planets, not really the Earth, because we're going to be spending sort of the rest of the semester talking about the Earth, but we really live in a golden age of planetary exploration. And so over the last 40 years or so forth, we've sent space probes to all of the different planets on Earth, or in our solar system, for the first time. And so these have gone from sort of specks that we see in telescopes to entire worlds that we can see, map out. We've sent landers to some of them, to sort of Venus and Mars. We sent orbiters into Jupiter, into Saturn, and so forth. But we've mapped the majority of these planets for the first time. And this has given us sort of an amazing sort of window into the diversity of our solar system. Okay, so we've got our inner rocky planets, outer gas giants. That's sort of the most important thing that you guys should remember here. Sort of further beyond that, you have the Kuiper Belt and the Oort cloud, and this is where a lot of comets and so forth live. Comets are basically leftover material from the formation of the solar system. A lot of these are composed of various types of ices in here. So if we see a comet in the night sky, it'll look like sort of a bright star, and then it has this basically tail that extends out from behind it. And this is due to basically ionization and melting of the ices in the comet. And these things sort of stream out behind it, and they're carried away from it by the solar wind in here. And these are thought to, people are interested in these because these are thought to be sort of your primordial solar system material in here. We've sent some space probes to these things. This one looks like sort of 2 dumbbells that are put together in here. You can see all of these rays coming off of it. This is material that it's basically outgassing as it gets closer to the sun in here. And then this material that sort of streams off of it turns into the big tail. So it's sort of amazing that we can send individual spacecraft, individual space probe, and go into orbit around sort of a comet like this. Okay, so Mercury is the planet that's closest to the sun. The sun is by far the most important body in our solar system from a sort of volumetric perspective. It's undergoing thermonuclear fusion. It's been burning basically for 4.5 billion years. It'll go for another several billion years of fuel left in it. This is a big giant solar flare. You could put the Earth basically inside there. So it's composed almost entirely of hydrogen and helium. Okay, so the first planet here is Mercury. Mercury doesn't have much of an atmosphere. And so it has fairly extreme temperatures. In some ways, it looks kind of like the moon here, but it rotates very slowly on its axis. People used to think that Mercury was tidally locked and didn't rotate at all, but it has basically one rotation per Mercury year. And it takes about 90 days for the Mercury to orbit the sun, and during that time, it has basically one rotation on its axis. But it has a daytime temperature of over, say, 230 degrees Celsius, nighttime temperature of negative 140 degrees. You can also see that the surface of Venus is characterized by all of these impact structures in here. There's a more modern image of it from Mercury's sort of messenger probe in here. So we've found, one of the things that this we found is that there's some water ice that exists in the poles of Mercury. We've also discovered that these things exist, similar types of things exist on our own moon in here. And so if we were going to go live on Mercury, basically you'd want to go to the sort of the polar regions in here. Mercury is mostly a dead planet, meaning it doesn't have sort of volcanic or tectonic activity in it, but there's some evidence that basically it's contracted a little bit as it's cooled, and we can see some of these sort of tectonic features on it. This is called like a wrinkle ridge. It's basically like if you take a sheet of paper and you sort of squish it together a little bit, you get something similar in there. Mercury, the composition of sort of your 4 terrestrial planets here is somewhat similar in that they've got a large sort of an iron core, a silicate mantle, and then a crust on them. However, the core in Mercury is particularly large relative to its size. So that's sort of a unique characteristic of Mercury. Venus, sort of your next planet in here, is almost the same size as and composition of Earth in here. But the big difference comes in the atmosphere of the 2 planets. And so if you look at Venus in here, you can't really see through the atmosphere. And the reason here is Venus has an incredibly thick sort of carbon dioxide rich atmosphere in here. And because of that, it has an extreme greenhouse effect. So the surface temperature of Venus is 480 degrees Celsius. It's like 700 or 800 degrees Fahrenheit. It's hot enough to melt lead in there. So this is sort of an extreme example. These photographs that you're seeing, they're not photographs, these are radar images of the surface of Venus. There are volcanoes on Venus. Venus is volcanically active. We've got a volcano here. These are probably lava flows, not active lava flows, but sort of somewhat recent ones in here. Now, one big difference sort of in the composition of sort of Earth versus Venus, you've got the atmosphere that's different, but on Earth, you have, the surface is divided into sort of your ocean basins and your continents. On Venus, you don't have that. You don't have continents on Venus. Basically, you just have all of your elevations that are distributed around sort of one basically average in here. And so there's no such thing as continental crust on Venus. And so rocks like granites are probably somewhat rare there. Okay, I'm gonna skip over the Earth. If we get to Mars in here, Mars is considered climatically the most similar planet to Earth. It's still not really all that similar, but if we were going to pick another planet that we had to go live on, Mars would be the one that we would go to. And this is the one that we've sent sort of the most space probes, the one that we have the most serious plans about ultimately sending somebody to Mars in here. So the year of Mars is 687 Earth days, so it's about twice as long. However, the Martian day, basically the speed at which it rotates on its axis, is about the same as Earth. And so that would be a familiarity. You'd have this similar sort of day-night cycle. Mars has ice caps on it, both on the North Pole and the South Pole in here. These are a mix of water, ice, and sort of carbon dioxide, dry ice in here. In the past, Mars used to have liquid water at its surface, and we can see the landscape has been carved to show evidence of this. However, now basically the atmospheric pressure is too low to basically sustain much in the way of liquid water. There may be some periodic basically melt events that happen that you might have liquid water that exists for a very short period of time, but then it sort of evaporates or sublimates into the atmosphere. This is the North Pole of Mars in here. It's mostly composed of water ice, but then there's dry ice or CO2 ice that sublimates basically every winter-summer cycle in here. We've sent a series of rovers to Mars. These are basically robotic geologists that have gone to the surface of Mars and sort of make investigations. They're equipped with cameras, they're equipped with devices that can measure chemistry of rocks and so forth in here. Sort of the two most active ones right now are sort of the Curiosity rover, which is in the Gale crater in here, and the Perseverance rover in here. And both of these are basically investigating areas that may have had water in the past. And so this is the Curiosity rover basically parachuting down to the surface of Mars in here. Parachutes only work part of the way down, and then when it gets close to the surface, it has basically retrorockets that fire and then basically land this rover. This is the surface of Mars in here, and in the Gale crater, there's a big mountain here known as Mount Sharp. This basically crater used to be a lake bed, and we can see sedimentary rocks on the surface of Mars in here that look similar to what we might see someplace on Earth. And so 3 billion years ago, there was liquid water on the surface of the Earth, of Mars, and it was thought to be much warmer. This is the same time period that life arose on Earth. There was single-celled life at the time, but people are investigating whether it's possible that life existed on Mars. So far, there have been no evidence of life, but sort of the search for this goes on. This is the Perseverance rover in here, taking a selfie. It also brought this little helicopter known as the Ingenuity helicopter that has been flying and taking some sort of aerial views of it. This landed in 2020 in a place called Jezero Crater that contains an active delta. Delta is basically the structure, sedimentary structure that's deposited when a river enters a lake. Basically, the water slows down and drops all of its sediment. And so many of the same types of geologic features that we see on Earth can also be found on Mars. Okay, so if we continue our sort of tour in here, after we leave Mars, we get to the asteroid belt, and there's a whole series of these. They're basically bodies that are left over from planetary accretion that exist in this area, and the gravity of Jupiter has kept these bodies from accreting into sort of a single planet. We've sent space probes that have gone into orbit and mapped out several of these in detail. One of them is this asteroid Vesta. It has a diameter of 525 kilometers. You can see it's not circular or spherical in here. It's sort of like a lumpy potato. And so it's not in basically hydrodynamic equilibrium. And what this means is that once planets get to a certain size, their gravity gets so strong that it pulls itself into a sphere. This body, because of its composition and its size, is not at basically big enough for that to happen in here. But it has an iron core and a silicate mantle, sort of like planets in the inner solar system. And so the space probe has taken some sort of very detailed photographs. You can see sort of craters and so forth on this asteroid. Another view of it in here. The largest body in the asteroid belt is the planetoid Ceres. This is considered a dwarf planet. It has a radius of 473 kilometers in here, so diameter of about 900 kilometers. The composition of Ceres, it has a rocky core and then this water ice mantle in here. And so it has a lower density than a lot of terrestrial planets. But a lot of moons that we see in the outer solar system have compositions that are similar to this in here. This is by far the largest body in the asteroid belt. And you can tell it has sort of this spherical appearance to it in here. Okay, if we continue on, we get to Jupiter. Jupiter is the largest planet in our solar system. It's a gas giant. It doesn't really have a hard surface to it, and its composition is similar to that of the Sun, primarily hydrogen and helium in here. It also has a really extensive moon system, series of moons that orbit it. So it's sort of a planetary system in its own right. It's a photograph from the Voyager 1 mission that flew by Jupiter in 1979. The Voyager spacecrafts are now sort of out of our solar system, and they're the furthest sort of human-created objects from the Earth. They're still basically sending back little bits of data and so forth. You can see the giant red spot. This is a hurricane. It's about the size. You could basically fit the Earth within this thing. This is a newer space probe, the Juno orbiter. This is taken of sort of a polar view of Jupiter, and there's all of these sort of spectacular sort of storm systems surrounding the pole of Jupiter. There's another sort of Juno image of this giant red spot, sort of a gigantic hurricane in here. Now, another thing about Jupiter is it's got extremely strong magnetic fields. And these magnetic fields produce radiation belts that can cook electronics on spacecraft. That would kill basically a person if you're in these radiation belts. And so the Juno spacecraft has this really sort of elongate orbit to sort of avoid the worst of these radiation belts, so the spacecraft doesn't get cooked in here. As I mentioned, there's a whole bunch of moons of Jupiter. The four largest of these are known as the Galilean moons. They were discovered by Galileo in the 17th century with some of the sort of the first telescopes. You can see these basically in orbit around Jupiter. The largest of these is Ganymede, and Ganymede is larger than the planet Mercury. We've got Io. It's the most volcanically active body in the solar system. We've got Callisto and Europa. Europa is an icy body in here. It's thought to have basically a saltwater ocean that exists beneath its surface. And people have speculated that this saltwater ocean might be a spot that life could be developed, sort of another potential body where life could develop in the solar system, although has not been found yet. So Ganymede in here has a density of around 2 grams per cubic centimeter. It's pretty close to Ceres. It has a composition similar to that. It's quite a bit larger though. It's a mean radius of 2,600 kilometers in here. Like I said, it's the largest moon in the solar system. It's bigger than Mercury in here. And it has a rocky core, water ice mantle, and then sort of an icy crust in here. Io is, like I said, it's a volcanically active body. It has a composition that's somewhat similar to the Earth. Somewhat less dense though, but it has an iron core, mafic silicate mantle, and then a silicate crust surrounding it. And the tidal forces on Jupiter sort of squeeze Io back and forth, and this causes sort of the interior parts of the planet to sort of partially melt, and then this causes sort of huge amounts of volcanic activity. And spacecraft have actually captured sort of volcanic eruptions. This is Io in here, and this sort of pimple at the top is actually a big giant volcanic eruption, an eruptive plume on it. So you can see the scale of some of these volcanic eruptions. We've also imaged active lava flows on Io. It's the only other planet that we've imaged active lava flows in here. Okay, so as we continue outward, now get to Saturn. Saturn is the second largest gas giant, the second largest planet in our solar system. It has these characteristic and spectacular sort of ring systems that surround it. Here's Earth in comparison to sort of the size of Saturn. This is just sort of the Earth placed next to it, so you can see the relative size of these things. And so Earth is pretty small compared to Saturn. We've sent dedicated space probes to Saturn. The most sort of recent one was the Cassini mission that was in orbit around Saturn, and it took images of Saturn itself, of the rings, of various moon systems in here. The rings of Saturn are composed of sort of water ice and sort of dust particles. There may have been some moon that was destroyed gravitationally and formed into these ring systems. One of the moons of Saturn is the only other body in the solar system that has basically a liquid at its surface, and this is the moon Titan in here. And so Titan is the largest moon of Saturn in here. It's about the same size as the Earth's moon in here, but a little bit bigger. And it has this thick atmosphere on it. It's very cold there. And it has liquid bodies at its surface, but they're not water. They're liquid hydrocarbons, like liquid methane and so forth. And so methane is natural gas. We use it for things like cooking and electrical power generation and things like that. But on Titan, liquid methane acts basically as water. And so it forms lakes, it evaporates into the atmosphere, it rains out there. Water basically forms rocks on Titan in here. And so the Cassini mission had a space probe that basically ejected off of it, and it parachuted down to the surface of Titan here and sent back these photographs. It's pretty amazing, actually. Here's the hydrocarbon lake in here. If we continue outwards, we get to Uranus in here. It's another gas giant. It has this sort of more bluish color. Also has sort of a series of moons around it. One of the unique things about Uranus is that its axis of rotation is tilted at 90 degrees to the rest of basically the planets in the solar system in here. And here you can see sort of its ring system that looks like it's basically on its side in here. Uranus is about 14 times the size of Earth. It's composed similarly of sort of hydrogen and helium, but there's a much greater sort of ice component, sort of water, ammonia, methane. That's why it has that sort of bluish color to it. Neptune is the planet that's furthest, or the furthest out of the gas giants in here. Sort of an interesting story about Neptune, that Neptune was predicted by gravitational, basically, perturbations in the orbit of Uranus. And so in 1846, people predicted using basically Newtonian sort of laws of gravity that Neptune should exist, or a planet should exist where Neptune was, and then astronomers looked for it and they found it in here. I was visited by the Voyager 2 space probe in 1989. That's the only space probe that's gone to Neptune in here. There's 13 known moons. The largest of these is Triton in here. And Triton has sort of this nitrogen and methane ice cap in here. There's nitrogen geysers on Triton. And so nitrogen, which is basically the dominant component of the atmosphere of Earth, is essentially like a magma on Triton because it's so cold there in the outer solar system. Triton is also compositionally in size pretty similar to Pluto. Pluto used to be the 9th planet, now it's demoted in here. And so this is a Hubble Space Telescope image of Pluto. Also has sort of the moon of Charon in here. And so up until about, I guess it's like 8 years ago now, these were the best images we had of Pluto in here. And so you had Pluto, and then there's sort of these series of moons in here. This is an image from 2012, about 10 years ago in here. However, in 2015, basically we had a space probe that did a flyby mission of Pluto and took some photographs of it. And so we went from knowing Pluto as basically a few pixels of light in these telescope images to having maps of the entire planet. And so this is what we know about Pluto now. It's an icy body in here, has sort of this lower density of about 1.8 grams per cubic centimeter in here, radius of 1,100 kilometers in here. This New Horizons spacecraft took some very close-up images of it. And so we've got these images of mountains on Pluto, which is a completely incredible thing if you think about it. There's basically mountains. This is a big sort of glacial plain that exists here. There seems to be some sort of basically like nitrogen snow cycle on Pluto. That's what all this white stuff is on sort of the tops of these mountains in here. And so there's an atmosphere that sort of forms sometimes when it's closer to the sun and then condenses on the planet when it moves sort of away from the sun. Eris is another body out in the Kuiper Belt. It's thought to be somewhat larger than Pluto. It was discovered in 2003, 2005. So the discovery of Eris is one of the things that triggered the demotion of Pluto from planetary status. And so the discussion was either you need to bring a bunch of these bodies and consider them planets, or you need to demote some of them, and basically the demotion people won out in here. But we can see that Pluto is basically a pretty spectacular world in its own right that has sort of complex geologic processes and so forth that are happening. There's a whole series of these trans-Neptunian objects, sort of like Pluto. We've got Pluto here, we've got Eris, but there's several other of these that are somewhat large as well. We've got Iris, Pluto, and then some of these other guys here as well. Okay, so that's the end basically of our tour through our solar system in here. So what you should know about our solar system, you should know how it formed. You should know this concept of sort of the solar nebular hypothesis. You should know a little bit of information about sort of each of the planets. We've got 8 major planets plus sort of your dwarf planets. The biggest split is between the inner rocky planets and the outer gas giants. That's probably the most important thing to remember. And then we have the sun, which is composed sort of hydrogen and helium and provides light and energy to our solar system through thermonuclear fusion. And with that, we are basically at the end of our lecture here for today. And so we talked about sort of the origin of the universe. There's a Big Bang theory. And then we went on a tour through our solar system. And so anyways, that's it for today. There will be a quiz posted on this lecture that I'll be sticking up on Canvas in here. And anyways, I hope you guys have a good rest of the week, and I will talk to you later. Bye.